Okay, welcome and thank you all for joining. This will be an old-fashioned talk in the sense that I will ask next slides to Jacob now and then. This is because of problems I encountered in upgrading my Mac to this Mac OS X Big Sur, after which Zoom, strangely enough, caused great problems. In any case, my title and my opening slides are, well, they go hand in hand. I wouldn't have chosen one without the other. Of course, there's a discussion whether Einstein's main objection to quantum mechanics was its indeterminism or its non-locality. I think the latter is true, especially in his later days. But there's no doubt that he was a staunch determinist. As a follower of Spinoza, he denied free will because of determinism, and he even used this as an excuse for his extramarital affairs. In any case, he here represents determinism, and of course, Godel represents undecidability. And what I will argue is that there is a certain tension between them, which I would say leads to the demise of deterministic hidden variable theories, as long as they accept the Born rule in any case. Jacob, next slide, please. All right, so I always advise my students to start their talks with the summary. So this would typically be a slide that's at the end in conventional talks, but I'll start with it. And that means that it's technical in a way that will unfold itself in due course. So if there are things that are unclear, I will hopefully explain them in the course of the talk. But this is the main point. So my claim is that deterministic theories underneath quantum mechanics, these are typically called hidden variable theories, but this word hidden variable sort of makes it too narrow. They're incompatible with the Born rule, provided we agree that determinism actually has two sides. The first side is the one that's totally uncontroversial and respected by all hidden variable theories I'm aware of, namely that each value of the hidden variable, which I call lambda, and in some cases also the quantum state, determines the outcome of any given experiment, which in this case will be a measurement of some quantum mechanical observable. But in addition, I require determinism to mean that the theory T, or any other theory invoked by T as an oracle, so to speak, could at least in principle provide the map that gives the value of the hidden variable or hidden state in any given experiment. And this is in fact not what typical hidden variable theories do, not even those called deterministic. So what they typically do is specify a probability measure on the space of hidden states, which is closely related to the Born measure or the Born probability, and then assume tacitly that a long run of experiments actually samples this measure in the sense that per experiment, a value of lambda is chosen and that the whole run samples this measure. But my argument hinges on the fact that you actually have to specify this map explicitly. And I will get back to this and motivate this argument in this assumption in great detail. Now, if you compare my claim in red with previous results, especially Bell's original 1964 theorem, at least interpreted in a way that makes it a constraint on determinism given quantum theory. There are many ways of looking at both Bell's theorems, but one valid way to look at his original theorem is that. And also later results like the free will theorem, also construed as giving constraints on determinism given the validity of quantum theory, or at least the Born rule. Such theorems obtain weaker conclusions from weaker assumptions, as you would expect logically. Namely, they do not fully, as you know, they do not fully exclude determinism. They leave two loopholes, namely deterministic hidden variable theories compatible with the Born rule should violate either what I call local contextuality, sometimes called parameter independence, or just locality. This is, for example, what Bohmian mechanics does. or it should violate what one could call free choice, which is an independence assumption on settings of experiments. And this is what, for example, Gerard 't Hooft's cellular automata interpretation of quantum mechanics does. But these theories, or these results, do not require my second clause. So they only require the theory T to provide this compatibility measure or probability measure mu, and then the results follow. So I have a stronger conclusion based on a stronger assumption, but this assumption I think is very natural and even necessary, as I will argue. Now the argument will be that the Born rule implies that quantum mechanical outcome sequences of experiments almost surely have a certain typicality property, which in logic is called one randomness, and which is closely related to Kolmogorov randomness, which I will explain. And then there is an instantiation, one could say, of Gödel's incompleteness theorems due to Gregory Chaitin, which states that most digits, in fact, infinitely many digits of such random sequences can, in fact, not be described by any standard mathematical theory, such as set theory, with or without the axiom of choice, in which a theory like T is described. So the theory T cannot actually give these digits. And that means that the theory cannot satisfy the second clause. The second part I take to be the definition of a deterministic theory. So this I will argue, and there's one sort of point we need to discuss, which is that the argument relies on the idealization of having an infinite series of measurements. So this is a vulnerability of the argument that I'll return to. Next slide, please. Right, so I'll give reasonably extensive background to this claim and also to the arguments I use. And I think it's natural to start the background with Max Born. So he introduced the probability interpretation of quantum mechanics. At least he was the first to put it in writing in a scholarly paper. And what he says right from the start is already decisive and great. So he writes, thus, he wrote it in German, of course. I translated this myself. Thus, Schrödinger's quantum mechanics gives a very definite answer to the outcome of a collision. I see that the slides have been mixed up a little bit. Let's go on. One obtains no answer to the question, what is the state after the collision, but only to the question, how probable is a specific outcome of the collision? And then he adds, this raises the entire problem of determinism. From the standpoint of our quantum mechanics, there's no quantity that could causally establish the outcome of a collision in each individual case. However, so far we're not aware of any experimental clue to the effect that there are internal properties of atoms, the later hidden variables, that enforce some particularly outcome. Should we hope to discover such properties that determine individual outcomes later, I myself tend to relinquish determinism in the atomic world. But this is a philosophical question for which physical arguments alone are not decisive. And it is in reply to this paper, which was, I think, published in the fall of 1926, that Einstein wrote his letter to Born in December 1926 in the Christmas holiday, which contains, well, his most famous words almost, quantum mechanics commands much respect. But an inner voice tells me that it's not the real McCoy. He says, De ware Jacob. You can argue about the translation. The theory delivers a lot, but it hardly brings us closer to the secret of the old man. Anyway, I'm convinced he does not play dice. And so, at least in this early stage, this is just about determinism. The locality issue came later. Next slide, please, Jacob. The second part of background to motivate my reasoning is of a more philosophical nature. It is supposed to introduce a way of thinking about randomness that is decisive even for my mathematical arguments and that played a role in my work. So I gave Born's words partly to highlight the fact that he opposes the randomness of quantum mechanics, and to be more precise, I think we have to call this surface randomness. So the only randomness I will be concerned with is the randomness of the outcome of measurements. So this talk has nothing to do with the measurement problem. I assume it's solved in the sense that measurements have outcomes, and I'm only concerned with actually lists of outcomes of measurements. Let's call that surface randomness. And that's also what Born was talking about, at least tacitly. So Born opposes this to determinism, whereas, for example, Laplace opposed randomness to something else, namely to complete knowledge in a deterministic world. That is different. And if you look back in history, earlier, say Aristotle opposed, well, his notion of randomness, which he called an accident, to purpose. So an accident, in his case, was failure of purpose. And Epicurus opposed his swerve, or the clinamen, to a straight course. And so this leads to a picture of randomness that was articulated by my philosophical colleagues, Christoph Lüthi and Carla Rita Palmerino, displayed here. Maybe some of you know them, since this is a Harvard seminar. In fact, Lüthi has a PhD in the history of science from Harvard. Palmerino is his wife. And they wrote a joint paper on the history of the concept of randomness, which concludes with the meaning of these terms, namely chance, fortune, randomness, etc., only becomes clear when one understands which alternative they exclude. So it's defined negatively. And then this I will combine with another take on randomness, which is Wittgensteinian, namely the idea of a family resemblance, where I give two quotes that I think make the point. One is from the Blue Book, in which he's still grasping for the concept, namely the idea that in order to get clear about the meaning of a general term, one had to find the common element in all its applications, has shackled philosophical investigation. For it hasn't only led to no result, but has also made the philosopher dismiss as irrelevant the concrete cases, which alone could have helped him to understand the usage of the general term. And later in the philosophical investigations, this sort of resolved by his idea of a family resemblance, which he used initially in the context of a game as his leading example, then of a language game, but I think which applies perfectly well also to the notion of randomness. Here, I'm saying that these phenomena have no one thing in common, in virtue of which we use the same word for all, but there are many kinds of affinity between them. We see a complicated network of similarities overlapping and crisscrossing, similarities in the large and in the small. I can think of no better expression to characterize these similarities than family resemblances. For the various resemblances between members of a family, build, features, colors of eyes, gait, temperament, and so on and so forth, overlap and crisscross in the same way. So if you combine take one and take two on randomness, the conclusion would be that the notion of randomness is, let's say, an antipodally defined family resemblance, which means it has a family of different meanings, which are defined and distinguished by their opposites, by their antipodes, by the alternatives they exclude. And this will be the basic philosophy of my entire talk. So next slide, please, Jacob. And so this slide contains my main reasoning, and all the rest will unfold it, so to speak. So the idea that randomness is negatively or antipodally defined family resemblance. Well, of course, if you look at all instances of randomness in all the sciences and in daily life and in world history, it's almost obvious, but it even applies to the narrow context of outcome sequences of measurements, even of binary outcome sequences. So I will specialize to fair quantum coin flips, such as 50-50 Born probabilities with just two outcomes, 0 and 1. And even to that very special context, you have this idea that there are many notions of randomness that compete with each other and are defined negatively. For example, one of the opposites would be Laplacian omniscience within deterministic physics. Another opposite, another antipode to the randomness of such a binary sequence could be computability. It could be compressibility, it could be predictability, it could be the existence of testable patterns, and literally, mathematically speaking, there are infinitely many other antipodes to the notion of randomness of a long or infinite binary sequence. All right, that's point one. Then deterministic hidden variable theories try to restore Laplacian determinism. I think that this is the underlying philosophy, in which, well, by definition, the chosen antipode to randomness is, as I just mentioned, omniscience within deterministic physics. And they try to do so by showing that quantum mechanical randomness is due to ignorance about the hidden state, in such a way that the single case probabilities that are empirically extracted from outcome sequences as long-range frequencies can be reproduced by a probability measure in the usual way, displayed here in blue. And if this can be done, and this indeed can be done for quantum mechanics, you could call an outcome sequence Laplacian random. And so this is just one of the notions of randomness that an infinite sequence can have. And it's a relatively weak one. It only sees or relates to the long-range frequencies extracted from the sequence. Now, if you look at Bell's theorem or the free will theorem, but especially Bell's first theorem, again, seen as putting constraints on deterministic theories, that shows that even in bipartite experiments, Alice-Bob, EPR-Bohm type of experiments, in fact, the outcome sequences are Laplacian random, provided you sacrifice something. So provided the theory that actually has this sort of Laplacian view of randomness sacrifices either local contextuality, as in Bohmian mechanics, or free choice, as in 't Hooft's theory. And so the conclusion of such theorems is that Laplacian randomness of quantum mechanical outcomes is what these hidden variable theories in fact can reproduce. But that's just one kind of randomness. And so within this general philosophy of randomness I advocate, there are other randomness properties of outcome sequences. And the key one for this talk, but there could even be other ones to which similar reasoning applies, but the one I will use here is that, as I will argue, so quantum mechanical outcome sequences, again, binary sequences for a 50-50 fair quantum coin flip, they are almost surely random in a much stronger sense than being Laplacian random. Namely, they're what is called one random in logic. So there's also, in fact, even two random, three random. There are other randomness notions I will not talk about. One randomness is the simplest one. But you can prove from the Born rule that the outcome sequences themselves have this randomness property. This is a theorem. And one advantage of this specific randomness property is that it's equivalently definable in three, well, apparently different ways. It has three different antipodes: compressibility and predictability and existence of patterns that turn out to coincide in this context. That makes this notion extremely attractive. And this is the randomness property that a deterministic hidden variable theory cannot reproduce. And this is what I will argue. So the earlier theorems a la Bell and free will focus on a randomness property of quantum mechanics that I would regard as relatively weak. And such theory, deterministic hidden variable theory, can actually accomplish this. But if you look at stronger randomness properties of outcome sequences, then they can't. That's my argument. Next slide, please, Jacob. Right, so just for those who are not so familiar with this, this whole literature on hidden variable theories and theorems about them, I would say initiated by von Neumann. So if a hidden variable theory T is asked to reproduce correlations, and I will now say is only asked to do that, of the usual way written down here in blue, and is asked to provide a probability measure given by the theory, making the statistical predictions of the theory compatible with the Born rule predictions of quantum mechanics, then these theorems like Bell's and free will, they basically come to the same conclusion, namely that the conjunction of four properties is inconsistent, namely determinism, but interpreted in only half of the way I would see as proper, namely the fact that these joint conditional probabilities are either 0 or 1, or in other words, that given the value of the hidden variable, the outcome of the measurement is fixed. The Born rule, local contextuality, which is also called parameter independence, and which is a locality condition in the sense Alice's outcomes are independent of Bob's settings and vice versa. And free choice, which is in a way more difficult to define, and which I will not try to do here, but it's an independence assumption. It states that the choice of the measurement settings in a certain sense is independent of the state of the particle or the system one measures. And in the case of Bell, that's actually relatively easy to define as stochastic independence. For the free will theorem, it's more difficult, but it leads to the same conclusions. And so if there's a contradiction between four properties, there are four minimal ways out, namely what to give up. And then, of course, mainstream, say, Copenhagen quantum physics gives up determinisms. Bohmian mechanics gives up local contextuality. Het Hoofd gives up free choice. And I think Anthony Valentini is one of the few people, but I follow him in this, who gives up the Born rule, which is another way out. All right, next slide, please. And so I will now sort of try to slowly zoom in on this notion of one randomness, which also has an interesting historical background, partly even related to the previous talk. So, you know, David Hilbert stated his problems in 1900, his 23 problems, of which well, many are relevant, in fact, to this story, but the most relevant one is the sixth, the mathematical treatment of the axioms of physics, especially the theory of probabilities and mechanics, which gave rise to three developments that are all crucial for us. Firstly, von Mises picked this up, so he wrote a short book, Foundations of Probability, Grundlagen der Wahrscheinlichkeitsrechnung, in which he tried to define the notion of a random sequence first. This turned out to be slightly flawed, but in a very fruitful way. And then try to derive probability, well, as a derived concept from that. Namely, probability for him was defined as a long-range frequency given the notion of a random sequence. And then Kolmogorov, inspired by the same problem, did exactly the opposite. So using the notion of measure theory, as you all know, von Neumann defined probability first and randomness second. And he himself realized that this did not work, that more was needed. Because of examples that were already known to Laplace, and I would say all mathematical probabilists, which in an example relevant to this talk, if you take the space that I denote mathematically by 2 to the power n, that means the space of infinite binary strings, also called the Cantor set or the Cantor space. So all these binary strings, they have the same probability, namely 0. And all measurable subsets, if you take this, they're generated by open sets of the type A sub x I give here. So if you have an infinite string that starts with an infinite sequence that starts with a given finite string sigma, and then extend it in any possible way, you get a subset of the Cantor space. And so the initial segment is fixed, and even these strings, these sequences, all have the same probability, and they only depend on this initial segment. So what this purely probabilistic idea does not see is the difference between sequences or strings that are sort of intuitively random, like this one, 0, 0, 1, 1, etc., or strings that are obviously not random, like having only ones or only zeros or 1, 0, 1, 0. So that was a problem with elementary probability theory already known to Laplace, that in fact Kolmogorov's formalism did not solve. And it was Kolmogorov himself who also led the way out through the notion of what is now called Kolmogorov randomness or algorithmic randomness, with which many other people were also associated. Solomonov, Martin Löw, Chaitin, Schnorr, and others. And just, well, almost for fun, I also mentioned von Neumann's 1932 book, Mathematische Grundlagen der Quantenmechanik, Mathematical Foundation of Quantum Theory. It's in the same line of historical development. It was also inspired by Hilbert's sixth problem. And in fact, with hindsight, it's surprising that it wasn't von Neumann who gave the measure-theoretic axiomatization of probability theory, that he left it to Kolmogorov, so to speak. Von Neumann knew everything about this, and he also knew the work of von Mises extremely well. But it was Kolmogorov who said both the first and the second step, so to speak. Next slide, please. So for those who want to know more about this, the classical works, mathematical texts on this notion of randomness are by Lee and Vitagni, and a much more difficult book by Downey and Hirschfeld. So Lee and Vitagni is mainly about randomness of long but finite strings. Downey and Hirschfeld is almost entirely about randomness of infinite sequences. But as a reading tip for the Christmas holiday, I advise a popular book by Diaconis and Skirms called 10 Great Ideas About Chance, which is not as popular as it sounds because it explains this development extremely well. I mean, it actually contains formulae, still written in a very nice style. This is a good introduction to the whole field, I would say. Next slide, please. Right, and so as I said, there are three equivalent ways to define this idea of one randomness, of which only the one via compressibility can be explained in a seminar. The other two are much more technical and complicated, and even this one is technical and complicated, but not in the worst possible way. But so the idea, firstly, about strings. So by my sort of standard terminology, a string is finite, set of zeros and ones, and a sequence is infinite. So a string is declared random if it has no shorter description than sigma itself, the string itself. But this is a paradoxical definition, since there's this Berry paradox, namely the Berry number is the smallest positive integer that cannot be described in less than 18 words. You will think about this for yourself in the break, and you'll see that this is contradictory. And so, as in many of these linguistic paradoxes, you have to specify your terms in order to avoid the paradox. And in this case, what has to be specified is the notion of a description. And this was first recognized, in fact, not by Kolmogorov, but by earlier people, namely Abraham Wald, who was the father of the relativist Bob Wald. I think he was the first to make this point, and this was then picked up by Kolmogorov. You have to make this entire setting computable, and then it works. So the Kolmogorov complexity of finite strings is done in terms of Turing machines, and for technical reasons, you have to use universal Turing machines that are so-called prefix-free. This is a technical point I could explain later, which is not so important, but otherwise the mathematics doesn't really work out. But in any case, the point is that finite strings are defined to be random if they're Kolmogorov complexity, which means the length of the shortest program run on a prefix-free universal Turing machine that actually produces these strings is approximately as long as the string itself, which means that you just effectively have to put the string itself into the program, and then you have achieved almost nothing, as opposed to the computation of pi, which is very long, but can be described by a very short program. So Kolmogorov randomness is the opposite. And this can be extended into the notion of randomness of infinite sequences of zeros and ones. This was first done by Chaitin and independently Levin, who was a student of Kolmogorov. And then the definition is that an infinite binary string is one random if there is a constant c such that each truncation, so s sub n, so s truncated to its first n digits, actually has a Kolmogorov complexity greater or equal than n minus c, which in fact implies that the Kolmogorov complexity continues to dominate n. That's an interesting theorem, but the idea is the same as in the finite case. And namely that the shortest description of the sequence is the sequence itself, but then it's done for each of its truncations rather than for the infinite sequence, because you cannot ask a computer program to output an infinite sequence. And then, so this is an interesting definition, and one of the first results by Martin Löw, who defined one randomness in an equivalent way using constructive measure theory, and then surprisingly showed equivalence to this definition, that if you have a pair of independent, identically distributed classical coin tosses, then the infinite outcome sequences are one random with probability 1, or almost surely, which means the same thing. So this notion sounds very technical, but on the one hand, I think it sort of captures the idea of randomness in the sense that a random object cannot be described more efficiently than by actually stating the object itself. And then it shows that this is generic, that this is actually the type of randomness that happens in coin tosses, for example. And another theorem about one randomness is what is sometimes called the monkey typewriter theorem, which is that each one random sequence contains any finite string infinitely often. So this is one of these results that drive you crazy if you think about it too long. So maybe I can ask for the next slide now.
I have a quick question, Klaas.
Yes.
You have a limit appearing there, sort of in the middle of this slide, that says the Kolmogorov complexity of the truncated first n letters of the sequence minus n goes to infinity. Is that limit correct?
It's a consequence of the definition, and it is correct. So what typically happens is that the Kolmogorov complexity of the nth truncation of the sequence is about n plus log n. And so the log n survives and goes to infinity, but it follows from the definition. It's not part of the definition.
Got it. Thanks.
Okay. And now the relevance for quantum mechanics is as follows. So there's a theorem that I think is completely uncontroversial. Namely that, although it's not so trivial to prove it, but the following procedures for repeated independent, identically distributed measurements are equivalent in a probabilistic sense, namely in giving the same possible outcome sequences with the same probabilities, namely either, this is, you could say, in Copenhagen style, either quantum mechanics is applied to the whole run via the tensor product in the usual way, and the whole run of measurements is actually seen as a single quantum mechanical measurement or experiment with a single classically recorded outcome, namely a sequence, that's equivalent to actually applying quantum mechanics to each single experiment with classically recorded outcome, say 0 or 1, upon which a classical probability is applied to combine them. And so this is the same, and either way, the de Born probability for single outcomes, so this is a workshop on the foundations of probability theory, so I should maybe declare my view, so I follow basically Lewis, maybe others, that a single case probability is a purely theoretical device that can be tested in long runs of measurements through the frequencies, the relative frequencies extracted from them. So if you take a fair quantum coin toss, then there's a 50-50 Born probability induces, let's say, the canonical measure on the space of these infinite sequences, with respect to which we speak of almost sure and probability 1. And so, as a corollary, for a fair quantum coin flip, like a measurement of a spin 1/2 system in the usual superposition of spin up and spin down initial state, has exactly the same probabilistic structure as a fair classical coin flip. And by the same theorem I quoted by Martin Löw, the outcomes of a quantum coin flip, a fair quantum coin flip, are almost surely one random. So far, so good. Next slide, please. And then the point will now be to apply a theorem, or maybe two theorems, due to Gregory Chaitin, which he himself saw as sort of the crowning achievement of the Godelian view of mathematics. That we could discuss about this for a long time, but let's state the theorems. So there's one for finite strings and one for infinite sequences. The one for finite strings is that for any given sound formal system, so the assumptions are very similar to the Godel incompleteness theorem. So for such systems, you can think of standard set theory, Zermelo-Fraenkel with the axiom of choice. It's not enough to think of arithmetic, because you have to sort of be able to state certain sentences, like the Kolmogorov complexity of a string is larger than n, and then this needs slightly richer mathematics than pure arithmetic. So it's good to just have set theory in mind, although that's too much in a way. But given any such sort of mathematical language as we all use, there is a constant C such that any statement of the type the Kolmogorov complexity K of sigma is greater than C, where sigma is a string, cannot be proved for any finite string, although it's true, in fact, for infinitely many strings. And then the version for infinite sequences is that it's not a trivial extension of it. It's also proved in a different way, namely that if an infinite sequence, or just a sequence in my terminology, if a sequence is one random, then such a system F can only compute finitely many of its digits. And in the literature, you will only find this for the most famous one random number, which is called omega, and which was introduced by Chaitin under the name of the halting probability. And in fact, all his thoughts revolve around it. But in fact, it's true for any one random system. This is not often stressed, but it's uncontroversially the case. And the proof is similar in both cases. So the finite case, so for strings, if you were to prove the fact that the Kolmogorov complexity is larger than a given bound, then the proof would in fact identify the string sigma. This is a non-trivial point. And from this identification, you could actually give a shorter description of the string than its complexity allows. So it's proved by contradiction. And also similarly for sequences, if you're actually able to compute too many digits, then you would compromise its randomness, basically. All right, next slide, please. This I'll skip. We started a bit late. We could leave this for the discussion if people are interested in the relationship between the Godel theorems and Chaitin's. So let's go to the next one. And now the argument comes. So my point that undecidability implies indeterminism. This is the following theorem, namely for any hidden variable theory T, which is supposed to state probability, at least is supposed to state probabilities for outcomes of experiments. So X here is the outcome of a measurement of an observable or a measurement with setting small a, given the value lambda of the hidden variable. Then the following properties of such a hidden variable theory T are contradictory, namely determinism as a double-edged sword, namely on the one hand, determinism means that these probabilities are either 0 or 1, so the theory is deterministic. And in other words, and this is a crucial reformulation that I will use and rely on in the next few minutes, this is the same as saying that actually the theory states or gives a function f from the space capital lambda of hidden variables to the space 2. 2 is just 0, 1. It's the bit underlying 2. So this fact that p lambda is either 0, 1 is the same as saying that actually t tells you, given the value of the hidden variable lambda, what the outcome of the measurement or the experiment is. So that's one uncontroversial ingredient of a hidden variable theory. But I also require, as I announced at the beginning, that the theory T states which lambda, which value of the hidden variable occurs in experiment number n. And again, I will argue why I think that this should be part of determinism. So that's my view, definition of determinism. And this is incompatible with the Born rule. Used either, as I said, you can use either the Born rule for the entire run of experiments seen as a single quantum mechanical experiment, or you do it case by case, it leads to the same result. And the proof of the contradiction is, well, it's not trivial because it relies on this Chaitin incompleteness theorem, but it's very easy, in fact. Namely, according to my notion of determinism, this theory T gives an outcome function. So if you compose the functions f and g, you get a sequence S, meaning a function from the natural numbers to the bit, to 2. Again, this underlined 2 means 0 and 1. And so T actually explicitly states the outcomes of experiments, but it cannot do so because, as I mentioned, did not prove, but mentioned, the Born rule actually implies one randomness of outcome sequences, and then by Chaitin's second theorem, only finitely many digits can in fact be described in some mathematical formalism of standard type in which typically physical theories are written. So this is an almost immediate contradiction. Could I have the next slide? And firstly, let's just do these two case studies that at least my intuition relies on and I think about all the time. So in Bohmian mechanics, the space of hidden variables is position space, either of a single particle or of a larger number of particles. Let's call it capital Q in all cases. And so my function g from the naturals to q just states the value of the particle positions in experiment number n. And this function s for sequence gives the outcomes of experiments number n for each n. And the probability measure that such a theory is supposed to produce to become compatible with quantum mechanics, at least in this Laplacian sense, is simply, it's literally the Born measure for Bohmian mechanics. So for arbitrary hidden variable theories, it can be more abstract. But for Bohmian mechanics, it is literally the Born measure for position, apparently introduced not by Born, but by Pauli even prior to Born's work. In the case of 't Hoofd, so the hidden variable is in fact a basis vector in a separable Hilbert space. So that is one way to rewrite his cellular automata theory, as he did himself, in fact. And so here the space of hidden variables is just the natural numbers, and my function g is just from the natural numbers to the natural numbers. And in his case, his compatibility measure is also the Born measure, but now not relative to position, but to just basis vector number n. So that makes these theories, in fact, very close to quantum mechanics because their compatibility measures are, in fact, just the Born measure. Now, if you contrast such theories with Copenhagen quantum mechanics, then one could say that Copenhagen quantum mechanics leaves individual outcomes to nature. So again, mathematically, these outcomes are sequences, so namely infinite binary sequences or functions from the naturals to the bit. And so they're, so to speak, unanalyzed. That's, you could see the essence of the Copenhagen interpretation, to leave the function as unanalyzed and provided by nature, so to speak. Whereas in the deterministic theory, it factors through the hidden variable space, lambda. That's the essential difference. However, both the Bohmians and also 't Hoofd, and I also believe other hidden variable theorists and theories leave the sampling that I call G of the Born measure also to nature. And they assume simply that their hidden variable, be it particle position or the state of a cellular automaton or anything, is in fact distributed according to their Born measure. And I will now argue, I'm almost there, that in that sense, I would say that almost nothing is gained over quantum mechanics, not even determinism. So could I have the next slide, please? And so the key question for me is actually who does the sampling of this Born or Born-ish measure? Again, the main point, I repeat this quickly because it is the main point, I think, of the discussion, that in deterministic hidden variable theory, so the outcome sequences, again, in this case, fair quantum coin flip, infinite binary sequences, in hidden variable theory, the outcome sequence as factors through a hidden space, lambda, as S is F composed with G for functions F and G. F tells you, given the value of the hidden variable, what the outcome is, and G tells you the value of the hidden variable in a given experiment number n. And so in such theories, this you could look, since F is uncontroversially given, I could state the argument either in terms of S or of G. Either one is supposed to sample the Born measure or the Born-like measure. And that means that the sampling process, if you look at it mathematically, that means that actually the sequences giving the sampling, again, telling either the outcome of the experiment or the value of the hidden variable in the given experiment number n, they should have a randomness property, reflecting the fact that you actually sample a probability measure. And one randomness is one of those. There are also other properties I could invoke, but one randomness is the best one in this case. And then there are two possibilities, trivially. Either this function G, again, the function that states the value of the hidden variable in each given experiment in a long run. Either it's provided by the theory, but this can't be because that contradicts this Chaitin incompleteness theorem, so that's impossible. Or it is not provided by the theory T. In that case, you could already argue that the hidden variable theory T fails to specify the outcome of individual experiments. And so what do we gain? But you could put it a little further. T cannot even invoke a deterministic oracle. It cannot ask another deterministic theory for the specification of this function G, because it would lead to the same contradiction. And therefore, these deterministic theories must, in fact, in order to do the sampling of their Born measure or Born-ish measure, they have to invoke an external random oracle. And it has to be random in a pure sense. It cannot be Laplacian random, because then again you run into the same contradiction with this Chaitin theorem. And so the necessity for these deterministic hidden variable theories to invoke external oracles that have to be random in the sense that they produce one random outcome sequences, which the theory itself cannot do, I would say make the claim that these theories are deterministic, self-defeating. And now, please, the next slide, and we're almost done. Where are we? Yes, so this reasoning we could discuss. What I see as the main vulnerability of my argument is the reliance on infinite sequences. And so I'm almost obsessed by what I call Earman's principle. I also used it in my work on the measurement problem and on phase transitions and symmetry breaking. It's a strong normative principle that I think sound reasoning in the philosophy of physics should adhere to. Namely, while idealizations are useful and perhaps even essential to progress in physics, a sound principle of interpretation would seem to be that no effect can be counted as a genuine physical effect if it disappears when the idealizations are removed. And so this, we could discuss the principle itself, but I agree with it. I think it's a sound principle. We should stick to it. And so in my case, the argument quite heavily relies on the idealization of infinite sequences of measurements. And so to sort of counter this threat and to satisfy Earman's principle, that there should be a similar argument that works for finite strings. So again, the mathematics works for infinite sequences in my case. And for finite strings, the argument becomes sort of more vulnerable. And the key point is that, I will not explain this entire slide now in view of the time, it's my last slide also. Instead of this second Chaitin incompleteness theorem, which was about infinite sequences, we now have to invoke the first one, his original one. The only thing he would himself call his incompleteness theorem, which is about finite binary strings. And if you want to rely on that incompleteness theorem for finite strings, it turns out that to make the mathematics work, you have to formalize in logic what it means for a deterministic theory to describe an outcome. And this apparently has not been done. And it's a very interesting problem where more research is needed. But in any case, it should be done in such a way that let's say, the new concept of a deterministic logical theory yet to be invented, that should in any case have the property that if such a theory produces a string, then it cannot be random in the sense of Kolmogorov, because indeed it has a deterministic description. And the cheapest way to resolve this problem, and then we're ready, but I mentioned this because then you know what the discussion is about. Suppose that in the context of binary strings, we identify determinism with computability, then the problem is solved immediately, because there is a well-known result in Kolmogorov complexity that a computable string cannot be Kolmogorov random. And then this entire problem is solved, but I think that the identification of determinism with computability is too easy. And if you're not ready to do that, so if determinism is seen as a sort of more general property than computability, then this is an issue that has to be resolved and where the thing is still incomplete. And I rely on the notion of an idealization for infinite sequences. Another issue, but let's leave this for the discussion, is whether deterministic theories can ever be falsified by finitely many experiments. I think the answer is no. But in view of the time, let's just go to the last slide, which lists some literature. Maybe there are some brief questions and we can move on. But thank you for your attention. I hope I managed to bring my point across. And for those who now see me drinking beer, it's 0.0. It's non-alcoholic.
Thanks, Klaas, for a great talk. All right, so it's actually just 3 minutes to the hour.
Yeah, I'm sorry for that.
It's no problem at all, but it means that just because we want to make sure people have a chance to take a break, if it's all right with people, if you could just hang on to your questions for the discussion period that will follow our last talk, which is Marcus's talk. So 1 hour from now, we'll have our general discussion time if you can hang on to your questions till then. I want to thank Klaas again for giving a great talk, and we'll take let's take a 3-minute break. We'll reconvene 1 minute after the hour. So on my clock, that's 2:01. I'm going to stop the recording and we'll get ready for our next talk. So Marcus, if you could stick around.
All right.